Here are the remainder of the lecture notes from our Organic 1 discussion in Chem 410. This question asks us which of the following is a 1,4 addition product of this reaction here. So a 1,4 addition product is pretty unique to dienes, as we see right here, and it really means that we've added something on the first carbon and the fourth carbon of the diene. And so we're going to look for a product that has the bromine on the end carbon. So A does not work for us. D does not work for us. That carbon is on the second carbon in, and there's two bromines added. We're going to add an H and a Br. So we know that we're adding H and Br, and we know that we need to add that H and Br in a 1,4 fashion. Another aspect of this is that the alkenes go away and they become a single alkene. And we know that because we can draw the mechanism like this. If we put this cation here, we now have a resonance stabilized cation. So we draw a resonance structure and we get this. Not as stable, but certainly still a cation that can undergo resonance. And so then the product becomes that. And we see that with C in this case. So C has one alkene that's moved to the middle of the 4 carbon chain and the bromine on the end. Alright, so which of the following here is the major cation rearrangement product of this reaction above? And so again, it will help us to remember the mechanism. So this is a proton transfer, and it ends up with something that looks like this. And then this is a secondary cation. We can rearrange that into a tertiary cation. And then the bromine can add. And so we're going to look for a product that has a bromine on the tertiary site and has no alkenes, because of course we added something to this alkene, and that's going to remove the alkene. So that means D and E are not good choices. C has a bromine on a secondary site, so that's not going to be the answer. B has bromine on a primary site. That leaves A. And as you can see, A has the bromine on this tertiary site here. Secondary alcohol is formed through oxymercuration, demercuration of which of the following? So we have to remember that oxymercuration, demercuration is simply addition of water in a controlled fashion. It doesn't allow for the formation of cations, and so it avoids rearrangement. It's still going to add the OH Markovnikov style, so the OH will go on the more substituted carbon. So in order to answer this question, it is probably useful to either envision or draw all 5 of these compounds, just so we know what they look like. So 1-hexene looks like that. Hexane looks like that. 2-methyl-1-bromopropane looks like that. 2,2-dimethylpropene. I think that's an error for whoever wrote this question. That was me. That should just be 2-methylpropene. You can't have dimethyl there. And then 1-hexanol is that. And really, the only possible answer that can undergo oxymercuration, demercuration is 1-hexene. That's the alkene. There's no other alkene, so these other 4 molecules will not react under these conditions, oxymercuration, demercuration. Okay, so here we have a question about TLC, and the goal here is to remember exactly what's happening with TLC. There's the plate that has some kind of group on it. Here it's an ethyl group. And then there's the liquid, the solution, or the solvent that's in the chamber that will move up the plate. In this case, it's 60% methanol, 40% water. So it's a rather polar solvent, and the plate is very nonpolar. So now we're going to spot each of these 4 or 5 compounds on our TLC plate, and we're going to decide which of them will travel the furthest. So if the compound has a high affinity for the plate, if it's very nonpolar, it won't travel very far. If it has a high affinity for the solvent, it will be picked up by the solvent and moved up the plate. So we just have to find the most polar of these molecules. B is not very polar. It is an ether. E is also not very polar. It has no functional groups except for the aromatic ring. And then we have an aldehyde, a ketone, and a carboxylic acid with a phenol. And this has 2 OH groups that has lots of hydrogen bonding, high degree of polarity. The ketone and the aldehyde also have decent polarity, but it's going to be the carboxylic acid and the OH group on the phenol that is the most polar molecule. And so that will travel the furthest during our running or development of this TLC plate. Alright, so we talked a lot about SN1, SN2. Now we're going to talk about E1. Remember that E1 is a reaction that starts by losing the leaving group to form the cation intermediate, and you'll have to remember which of those types of cations are most stable. We talked about that last night. So which one most readily undergoes E1? That's probably going to be the one that forms the most stable cation. So this one here will form a secondary cation. This one will form a primary cation. That'll give us a tertiary cation. That'll give us a secondary, and that one's primary. So there's only one tertiary. That means that that is the most favorable substrate for E1 reaction. So here we see a reaction. There's an alkene that's being turned into a primary alcohol. So there's an alcohol that's being added to this carbon, and then of course the second carbon is turned into a CH2 instead of a CH. So we're adding water. So we're essentially adding water across this double bond. This is a hydration. So we need to remember which of these reagents will allow us to perform a hydration. The base will not do that. Base won't react with alkenes. Water and peroxides, we have not learned a reaction that involves water and peroxides. Water and H2SO4 will do a hydration. However, this proceeds with a cation intermediate. And so it would go Markovnikov. And if you remember what Markovnikov addition is, it would give us the most substituted alcohol, which in this case would be a secondary alcohol. If we add the OH to the second carbon in, we'd get a secondary alcohol that's more substituted than this primary. So D will also not do this reaction for us. And then we have this mercury reaction, and then NaBH4. That is alkoxymercuration reduction, and that also proceeds by Markovnikov addition. It just doesn't have a carbocation intermediate. So that only leaves B as our reaction. And maybe you remembered this, the hydroboration oxidation. That is a method to put the alcohol on the least substituted of the alkene carbons, and that's actually my favorite reaction from Organic 1. So this one is the only way we know how to put an alcohol on that carbon. Alright, here's an alkyne reaction, and we're asked to predict essentially the major product, and that's a pretty common question that we see in organic chemistry. So we have this alkyne in the middle of a 6-carbon chain. We have some sodium metal and liquid ammonia. And this is a special type of reaction. This is called the dissolving metal reaction. Essentially, it helps us to reduce the alkyne into an alkene. So we're going to look for alkene products And so that's an alkyne. That's not going to be the answer. B doesn't have any alkenes in it. It also doesn't have any alkynes in it, so that's out. And E, the ammonia, only serves a role as a proton source and as a means to dissolve the sodium. So that leaves us with C and D. And these are both the same. They have the alkene in the middle, coming from the alkyne. It's just a matter of deciding whether we formed the cis or the trans in this case. And if you remember, this mechanism it proceeds under a radical mechanism. But if we think about it, there's our hexyne. If we add an electron to this hexyne, we get something that looks like this. We have a negative charge with a lone pair, and then we have a radical down on the other side. So we've essentially split apart the alkyne. We've created a negative charge with a lone pair. And so I've drawn this in a trans fashion. That's because the electrons desire to be as far apart as they can from each other. And that's going to be the trans instead of the cis. And so that leads to the trans product being formed in this case. If we want a cis product, that's when we use H2 and a poisoned catalyst like Lindlar's. That will give us the cis product where the H's are added to the same side of the alkyne. And the last one, here we're adding HBr in excess to an alkyne. It's very similar to adding HBr to an alkene, except of course, as we discussed in class, we have 2 pi bonds that can react with HBr instead of just 1. And in this case, it's going to be Markovnikov addition. We would expect the Brs to be added to the more substituted carbon of the alkyne, and indeed we'd expect both of them to be added to that side. And so, because it's excess, we know that we're going to add more than 1 Br, and we can cross off B. We know that the Brs will add to the same side because they will form the most stable carbocation twice. So that's going to be this one. This carbon forms a really stable cation because it's next to the aromatic ring and it has a lot of resonance possibilities. So in this case, adding excess HBr to this alkyne gives us the product we see in A.